Okay, now let us design the FIR filter using frequency sampling method. So FIR filter design using frequency sampling method. Okay. Now there are various methods of designing an FIR filters. Most prominent are the frequency sampling method, the windowing method, and the optimization method. So in this part of the lecture, we shall study the design of FIR filter using frequency sampling method. Now basically, the design follows some simple step. First, we obtain the desired frequency response, say HD, D being desired, e raised to j omega, and convert it to HD of k by means of frequency sampling. Let's see, sampling, otherwise known as DFT, discrete Fourier transform. If you recollect from the previous videos on DFT, we essentially did frequency sampling. So we sample the frequencies in the frequency domain in order to derive DFT from DTFT. So in order to sample the frequency, let the frequency is sampled by n total number of samples. So in this case of omega will become twice pi k over n, which was our condition for DFT. Okay. Then what we need to do is from HD of k, we go to the impulse response h of n, which is done through, from HD of k, we go to the impulse response h of n, which is done through inverse DTFT. And as per the formula of inverse DTFT, we can write h of n to be equal to 1 over n summation, where k goes from 0 to capital N minus 1 h of k, or you can write HD of k, it's just notation, Wn minus of nk, where obviously in case of DTFT, n goes from 0 to capital N minus 1. So what we have essentially done is that h of n will have a finite number of samples, which in our case is n samples. So previously HDE to the j omega was having infinite number of samples. So what we have done through these two steps is essentially made the number of samples or the number of frequency components to be finite. Now then, there are basically two types of frequency sampling. sampling. There are two types. The type 1 frequency sampling, and there is the type 2 method of frequency sampling. So we shall be mostly concerned with type 1. Now type 1 is inclusive of omega equal to 0. That is, in solving type 1, we must include omega equal to 0, and you have guessed already, type 2 is exclusive of omega equals to 0. So for that reason, we shall be concerned with type 1. So let us go to the step. So the first step, step 1, is we sample the frequency omega equal to twice pi k over n, where this n is known as the order of the filter. That is, how many orders of filters that is required to get to a required transfer function. And obviously k in our case goes from 0 to n minus 1. Now step 2 is to replace or determine hd of k, which is equal to hd of e to the j omega, where omega is equal to twice pi k over n. So after applying IDFT, so applying IDFT, we get h of n, which is equal to 1 over n summation, where k goes from 0 to n minus 1, hd of k, wn minus of nk. So here comes the difference with DFT and frequency sampling method. So our task will be that our coefficients of h of n will always, or shall I say must always, have real values. So our concern is that the coefficients of h of n must always have real values. So this brings us to the third step. So for real value of h of n, there is a specified formula. So h of n, in order to get real value, this will be, the IDFT will be 1 over n h of 0 plus 2 times summation k goes from 1 to p, the real part of h of k e to the power j twice pi k n over capital N, and where p is equal to n minus 1 by 2 for n when it is odd valued, and n by 2 minus 1 for n being even valued. So these are our basic steps in order to determine the transfer function of FIR filter using frequency sampling method. So enough theory, let us look upon an example. The concept will become much more clear like that. So the problem dictates determine the impulse response. Determine the impulse response that is h of n of a filter having desired frequency response hd of omega e to the power minus j n minus 1 by 2 omega for 0 less than equal to omega less than equals to pi by 2 and 0 for pi by 2 less than equal to omega less than equals to pi. So this is our given problem where n is equal to 7 using frequency sampling approach. So this is our complete problem. In all the problems, you must look for the value of n or the number of total samples and the desired frequency response. From that, you can easily derive the impulse response using the frequency sampling technique. So let us go to the solution. So first of all, here our desired frequency response hd of omega is equal to e to the power minus j, n is 7, so 7 minus 1 by 2 omega, which equals e to the power minus 3j omega, when omega or absolute value of omega goes from 0 to pi by 2, and it is 0 when omega is bounded by pi by 2 to pi. Sorry, there seems to be an absolute value. Now let us go to the first step. So in order to calculate h of k, first we need to calculate omega, which will be equal to twice pi k over capital N, so twice pi k over 7, where k will go from 0 to 6, n minus 1, since n is 7, so this will go from 0 to 6 in our case. Moving on to step 2, we simply replace hd e to the j omega, where omega equals to twice pi k over 7. Replace the value of omega in this function in order to derive h of k. So h of k will be equal to e to the power minus j 6 pi k over 7. Just replacing the value of omega by this quantity. For 0 less than equal to omega being twice pi k over 7 pi by 2. Is it not? Just replace omega with twice pi over 7. 0 for pi by 2 less than equal to twice pi k over 7, which goes to pi. Now before moving any further, first we need to evaluate the boundary limits for h of k. So one thing that needs to be addressed is that here the function variable is omega, and hence we are giving the boundary limits for omega over here. But in this case, the function the function variable is k. So it is quite obvious that the boundary condition must limit the values of k. So we are going to do that. So in this case, the right hand side will remain same. So let me write it down, e to the power minus j 6 pi k over 7. We just multiply by cross multiplication. So in this form of inequalities, 7 will be multiplied both in this side and this side as well. So 7 times 0 is 0. 7 times pi by 2 is 7 pi over 2. And similarly, twice pi will get multiplied in this direction and this direction as well. So 0 divided by twice pi will be 0. So the left hand side will remain 0. And in the right hand side of this inequality, previously 7 went there. This was 7 pi over 2. So 7 pi over 2 and divided by twice pi will become 7 over 4. And this part will become simply k, because we have taken twice pi and 7 pi and cancelled each other out. Similarly, for 0, we need to do the same thing. Just simply multiply 7 in this direction, twice pi. Just simple cross multiplication, but in this case, we need to do it in both sides of the inequality. So this becomes 7 by 4 k 7 by 2. So now points to be noted. K dictates the number of samples, and the number of samples can never be fraction. It must take integer value, and the integer value must be upper bound of 7 by 4 in this case, and 7 by 2 in this case. So let us determine what is 7 by 4. So using the calculator, 7 divided by 4, this is equal to 1.75, and 7 divided by 2, this will be equal to 3.5. So in order to bound k, we need to make this integer. So in order to make this integer, we must take the upper bound of this value to be 2 and this value to be 4. Otherwise, if we have taken the lower bound, that is 1, what would have happened is that we cannot completely bind. So this 0.75 of the remaining part of the sample will miss some of the information of this signal. That's why we shall always be concerned with the upper bound value. So let us replace. So e to the power minus j 6 by k over 7 for 0 less than equals to k less than equals to 2, 0 for 754 we have determined it to be 2 and equal to k less than equals to 4. So let us give this equation number 2 and we give this equation number 1. So the second step is also done. We have derived h of k. Now for the third step and the final step, what we need to do is determine the impulse response for the real coefficients. 1 over n h of 0 to the real part of h of k e to the power j twice by kn over capital N, and p will be equal to n minus 1 by 2 for odd and equal to n by 2 minus 1 for even. So since in our case n is odd, since n is odd and equal to 7, so p will be equal to 7 minus 1 by 2, which is 3. So we can simply rewrite this equation to be equal to before that we need to determine the value of h of 0. So let us do that. Okay, so from equation 2 we get h of k to be equal to e to the power minus j 6 by k over 7, and so h of 0 will be equal to, just replace this value with 0 and this will result to be equal to 1. So now we can determine h of n to be equal to 1 over 7. This is the value of 1 over n. H of 0 we have determined it to be 1 plus 2. There is a limit where k goes from 1 to p, summation the real part of h of k e to the power minus j twice by kn over 7, because 7 is the value of n over here. Now, another point must be noted is that we got the value of p to be 3. So 3 is the total number of samples, and for that reason k will go from 1 to 2 over here. And this is because if you look at the limit, for this value that we are working with, k goes from 0 to 2. So although there are 3 samples, we must discard the third sample because k is bounded up to 2. So I hope you get that. Now, doing some algebra. 1 over 7, this becomes 1 plus 2. Summation k goes from 1 to 2. Re h of k given over here is e to the power minus j 6 pi k over 7 to the power minus j twice pi kn over 7. Okay, 1 over 7, 1 plus 2, summation, the real part of, just multiply these two exponents, e to the power minus j, taking twice pi k over 7 as a common factor will leave us 3 minus n. Obviously k goes from 1 to 2. So now what we need to do in order to get the real part is just expand this exponent using the Euler's relation. So we get 1 over 7, 1 plus 2, the real part of cosine twice pi k over 7, 3 minus n, minus j sine twice pi k over 7, 3 minus n, where k goes from 1 to 2. Now since we are considering the real part only, so this whole part will become 0, or otherwise you can say it will be cancelled. So we will be left with h of n 1 by 7 plus 2 summation, where k goes from 1 to 2 cosine of twice pi k 7, 3 minus n, where n goes from 0 to 6, which is our required impulse response. Now what we need to do is determine the values of h of 0 through h of 6. So in order to do so, we expand this summation operator, 1 over 7, 1 plus 2 cosine of twice pi 7, 3 minus n, cosine of twice pi times 2 over 7, 3 minus n. So this is our expanded sum. So for n equals to 0, h of 0 will be equal to 0.06, n equals to 1, h of 1 will be 0.18, n equals to 2, h of 2 will be 0.26 equals 3, h of 3 will be 0.71, n equals 4, h of 4 will become 0.26, equals 5, h of 0.18, n equals 6, h of 6 will become 0.06. Now the question is, how do I get this value? Just simply use the calculator. Type this whole entire equation in your calculator and replace this with some variable, let's say x or y or z that is shown in that is provided in the calculator, and just plug in the value 0, 1, 2, 3, 4, and the calculator will do rest of the work. So if you have any problem, just tell me. I'll make a video on it, how to calculate these values. So one important thing that must be noted is that in order to verify that your result has been correct, is that in case of FIR filter, the first value and the last value will be same. The second value and the second to last value will be same. The third and the third to last will be same, and there will be a median value. So the value will follow something like this, a Gaussian distribution in case of the FIR filters, whatever technique you may use. So this is a basic recheck of the mathematical problem that we have done. So this is our required answer, by which we have solved the FIR filter impulse response using the frequency sampling approach. In the next video, we shall learn about the FIR filter design using windowing techniques.